Hello, and welcome back to the Mechanochemistry discussions. This seminar series is hosted by the NSF-funded Center for Mechanical Control of Chemistry, or the CMCC. I'm Ashley Martini. The goal of the seminar series is, as always, to bring the community together. Our seminars stream live on the third Thursday of every month at 11 a.m. Eastern. They're also available to watch anytime on our YouTube channel. I encourage you to check out the YouTube channel to watch the presentations from all of our previous excellent speakers. We also have some excellent speakers upcoming, and we hope that you will join us for all of them. Before we get started, a great big thanks to a few people. First, Dr. James Batiste, the Center Director, Jennifer Belsick, the Center's Administrative Coordinator, and two CMCC students without whom the seminar would not be possible, Quintarius Moore and Katie Floyd. Thank you ahead of time so much for joining us. Please do subscribe and follow us on YouTube as well as on Twitter. And also, last thing before we get started, a reminder that this webinar is being recorded. But if you have questions during the presentation, you can email them to us at cmccdiscussions@gmail.com, or you can post them directly into the YouTube. And either way, they will be propagated to the speaker at the end of the presentation. And without further ado, it's my pleasure to welcome today's speaker, Dr. Adam Michalchuk. Adam is an assistant professor in physical chemistry at the University of Birmingham and is an international Wilhelm Ostfeld Fellow at the Federal Institute for Materials Research and Testing, the BAM, in Germany. He's originally from Canada. Adam studied in the University of Edinburgh and Novosibirsk State University in Russia, from which he obtained his PhD in theoretical solid-state chemistry in 2019 and experimental solid-state chemistry in 2018, respectively. Following his PhD studies, Adam took up a postdoctoral position at the BAM and a guest scientist position at Free University Berlin, continuing to work closely at the interface of experiment and theory. In the summer of 2021, Adam was appointed as a senior scientist at the BAM in the Department of Materials Chemistry before taking up his current position in Birmingham in October 2022. Adam's research activities span various topics relating to the mechanical reactivity of solids, ranging from fundamental theoretical developments to high-pressure science and the development of new methods for monitoring mechanochemical reactions in real time. Please join me in welcoming Dr. Michalchuk.
Right, good morning or afternoon, wherever you are. Thank you very much for tuning in. So my name's Adam Michalchuk, and I'm from the University of Birmingham in the UK. So before starting, just a quick thanks to the organizers, so Ashley Martini and James Batiste, for the kind invitation to contribute to this series on mechanochemistry. It's been an absolute pleasure watching it, so it's really quite an honor to be able to contribute my own snippet to this series. So thank you very much. Right, so over the next sort of, I guess, half hour or so, I just want to introduce some of the work that we've been thinking about and some of the work we've been doing over the last few years in trying to understand sort of the dynamical aspect of mechanochemistry in the solid state, so not in polymers or other more complex media. So before starting on the science, if anyone wants to run away, this is all I'm going to try and teach you in the next half hour. So I'll start with the end, and then we'll get into the nitty-gritty details. So I think it's probably no surprise to anyone in this audience that one of the big aims that we're trying to achieve in the community is to learn to control mechanochemical reactions. You know, it's this wonderful game-changing technology where we can do reactions without solvent, but we're still at the point where we're trying to learn to control them. And I think in order to achieve that, we really still need to answer a lot of questions about how these reactions are happening in the first place. So that's sort of our overall aim. From my perspective, I think one of the sort of complicating factors is that mechanical force can play a lot of different roles in a reaction depending on the type of system that we're dealing with. That is to say that there may be different types of mechanochemical reactions, and we need to start to think about what those different types are in order to get to grips with what mechanical energy is actually doing in a particular system. And then in that way, if we can identify what the mechanical energy is doing in a particular system, we can start to think about how we can manipulate the system in particular and give us that degree of control that we're interested in achieving. What I'll hopefully show you that some of these mechanical effects are quite macroscopic, and that we can start to study these quite well using time-resolved in situ methods, and whereas a lot of other mechanisms are really quite microscopic. At the moment, both our group and other groups around the world are trying to study these using atomistic simulations, and I'll show you a little bit on what we're doing in that area. So just for completeness, I'm sure I don't need to introduce everyone to what mechanochemistry is, but why not? So I know we're all very familiar with chemistry across the traditional landscape. We know that we can drive chemical reactions forward with thermal energy, electrochemically, with photochemical reactions and magnetochemistry. But it wasn't until really the end of the turn of the 20th century that people started to recognize that actually mechanical force is another way to do chemistry. And it was a bit strange that it wasn't until that sort of late progress in human history that we recognized that this was a technology for driving chemistry. Because actually, if we dig back in our own history, it was our ancestors that used mechanochemistry right at the very beginning to create fire. And so actually you could say mechanochemistry gave birth to modern society as we know it. And actually, there's evidence of mechanochemistry in various aspects over many, many centuries. We've been using mechanical treatment of materials for millennia to try and extract ores from rocks and from other minerals. And we've been using it also in sort of, I guess, ancient pharmacy, if you want, to try and create poultices and other sort of medical remedies. So we've been treating these solids using mechanical force for forever. But in the modern world now, we're starting to recognize that actually mechanical energy is really, really useful, both technologically and in the chemical laboratory. So one thing I think is important to recognize is that mechanochemistry really has a lot of facets to it. Our ability to control chemistry and technology with mechanical force has lots of different dimensions. So on one aspect really is technology. We have a lot of materials, say explosives and energetic materials that respond quite dynamically, I'd say, to mechanical strain. So whether it's explosives or using safety mechanisms in cars or even pyrotechnics for entertainment purposes, these are all mechanically responsive and reactive materials. And we use mechanical energy to process a lot of things we use in our everyday life. So whether it's in the pharmaceutical industry, we need to mechanically process our powders, we need to compress those into tablets. That is mechanochemistry to some degree. And many of us won't get out of bed in the morning without a cup of coffee. And of course, that's generated by processing our coffee grinds mechanically, grinding them up to increase the solubility and actually make something that we can drink. So again, mechanochemistry is really all around us. But what we're starting to realize more and more, I guess, in the chemical world is that we can use this not just for interesting technologies, but really in chemistry to replace a lot of potentially toxic solvents or replace a lot of slow and inefficient reactions on the lab bench. So what we can really do is we can take our powders, we can stick them in one of many devices, and we can apply mechanical loads to that device, and that then allows us to push chemistry forward, or the reaction forward. So really, I think an enormous breadth of applications to this mechanochemical world. But hopefully what you start to recognize very quickly is that these systems are very, very different. The applications are very, very different. And perhaps not surprisingly, the mechanisms of what mechanical energy is actually doing in one system or another is also quite different. So if we think of that maybe a bit more philosophically, we can start to think of what does mechanical energy actually do to a system? So in one case, what we'll probably find in a lot of cases, particularly with organic solids, is that the mechanical force is likely to be there really just to enhance mixing. So that's going to be, for example, mixing the particles around. That's going to be comminuting the particles, making these particles smaller. That's going to be refreshing surfaces and actually generating new reactive contacts. And that might also be to create sort of friction at surfaces and heat the surfaces. So to enhance the fluidity of the material and allow the molecules to come into contact with one another. We're going to have other cases where we are using mechanical energy actually to make the solid itself more reactive. So this is something such as mechanical activation, where we're introducing defects into the system, or we're activating a surface of some form, or it could be where we're applying a mechanical strain and we're increasing or we're changing the underlying potential energy surface of that system and allowing chemistry to evolve in a very different way. Then we have this other class, which I think is where we get the mechanical energy that directly couples into the electronic degrees of freedom in our system and actually directly drives the chemical reaction itself. So if we spin it out that way, and I certainly don't claim that these are the definitions of different types of mechanical action, but it's at least the way that I'm starting to think about this. But if we span it out this way, what I hope becomes clear is that we have certain processes where the mechanical energy is acting at a relatively macroscopic level. We're mixing particles, we're comminuting particles, and then we have other areas where the mechanical energy is acting at a very elementary, very microscopic level. So we really need to kind of get to grips with what mechanical energy is doing across these scales of length, and learn which systems are going to respond in certain ways to the mechanical energy. So just to highlight what I mean by these different areas, so I'll start with the macroscopic side, this sort of mixing. And I think in this sense, the resonant acoustic mixer, so this new device here on the left is really a beautiful example of this, where we essentially apply an acoustic field to a powder, and that acoustic field breaks within this powder and causes a shear mixing between these particles. So there's no milling balls, there's no other sort of milling media, it's really just particles that are mixing past one another. And it turns out in many cases, we can actually use this to drive chemistry forward. So an example that we did a couple of years ago was just the co-crystallization of carbamazepine and nicotinamide and the presence of a small amount of water to form this one-to-one co-crystal here. So I'll touch more on this later, but we did some in situ measurements to see what was going on. And what we found is that if we take, if we do this mixing at very, very low energy, so very low intensity mixing, we actually form not the co-crystal, but we get a reaction between the carbamazepine and the water to form a hydrate phase, and the reaction stops. But if we increase the intensity of that mixing, if we really force those particles past each other at quite some high intensity, we first form the dihydrate, but then that gets consumed and we finally get to the co-crystal phase. So again, just by changing the intensity of the mixing, we're able to change the reaction profile. Now, that maybe isn't so surprising if we think about how reactions happen in the solid state. Our reaction is not going to be defined by the total amount of material in our system, but is really going to be defined by the structure of the interparticle contacts. So what we find actually is that at low intensity mixing, when we start to form this dihydrate compound, and it actually forms coats around the particle, and it stops us being able to form new reactive contacts between the nicotinamide and the carbamazepine, and the reaction stops. We can't get more reagent there to cause the reaction to progress. But if we go to higher intensities, we actually found that we're able to break off that coating, refresh the surfaces here, and re-expose the reagent to the carbamazepine and push that reaction forward towards the co-crystal product. It's a very simple example, but I think a very clear example that mixing in many cases is really quite enough to cause these reactions to happen. But then that does start to ask the question, if we're just mixing our particles, actually, how is a reaction happening? And I think that that's a very, very complex question, but I think one of the main ideas is we need to fluidize the solvent, the material. We need to fluidize somehow the surfaces of these particles. So one obvious way to do that, of course, is heating. So we know from various measurements that there is some heating in mills, in various mechanochemical devices. There's going to be frictional heating between particles. This is just a very quick measurement of some of the heating rates in a particular P23 mill. But we know there is some heating. And it turns out that organic solids tend to have quite low melting points. And actually, there's a lot of cases out there where we have what's called a eutectic, where we can actually depress the melting point by combining two materials together and actually get much lower melting points than you could otherwise expect. So this was a really nice example by Paolo Mazzeo at the University of Parma, where he showed that indeed a mechanochemical co-crystallization passed entirely through very, very small amounts of heating and the formation of a eutectic and the subsequent crystallization from that eutectic. There are other cases, again, particularly in the organic community, where we have highly hygroscopic compounds. And what we find actually is that although you might put dry components into your ball mill, they tend to absorb water from the atmosphere, and they create very small amounts of liquid on the surfaces, and that's enough to facilitate this fluidization. So we had an example a couple of years ago, and then there's been an absolutely beautiful example by Helena Shepherd at the University of Kent very recently, who again showed a solid plus solid reaction occurs through dissolution in absorbed water from the atmosphere. So again, what we're doing here is we're bringing two particles together, we're fluidizing the interface, and we're allowing the chemistry to happen in some fluid state. Now, these are certainly not the only ways we can get fluidization. There's lots of different origins for fluidization, and we've discussed it in some detail in a recent review. So do take a look, and I'm sure there's plenty of others that others can think of for how these processes could happen. So if we move then on to the activation stage, so we know again from historical literature that effectively what we're doing in a powder processing sort of process is we're taking our particles, we're mechanically treating them, they're being reduced in size, and at some point we can't reduce that size anymore, and subsequent mechanical treatment effectively leads to formation of defects within these crystals. And if we can, so that effectively stores energy in these crystals, and we can then change the reactivity in that way. So there's a really nice example, now over 20 years ago, on this silver oxalate system, where they were looking at the thermal decomposition of this inorganic species as a function of mechanical activation. And effectively what they found is that in the absence of mechanical activation, the thermal decomposition is very, very slow. But after mechanical activation, the decomposition rate increases quite significantly. So we're enhancing the reactivity of this compound by storing that mechanical energy inside that crystal lattice. But what's more, they didn't just find that the reactivity increased, but they also found that the reactivity changed. The actual chemical reactivity was altered by this mechanical activation. So whereas in the non-activated state, they found the formation of carbon dioxide on thermal decomposition, actually in the activated state, there was a mixture of gases formed. So again, not only do we change the reactivity, we change the chemistry as well. Very recently, we've shown this also for organic systems. So we've looked at a polymorphic transformation between this green polymorph and this blue polymorph. There's a large induction period, and we wanted to understand, does that have something perhaps to do with activation? And so through a combination of DFT and thermal analysis, effectively what we were able to show is that this induction period is associated with the activation of our materials. We are seeing an increase in the amount of energy stored in these crystals, and that leads up to this transformation. So again, we're systematically destabilizing some system until we overcome some threshold and push that reaction forward. There's also a lot of literature out there where we're applying mechanical fields that are essentially stationary, and we allow the system to adopt a new geometry under that mechanical strain. So this is an example we did in high pressure chemistry a couple of years back now, where we looked at the compressibility of this coordination polymer. And what we found actually is that there is a structural transition in this material as a function of that compression. And again, through combination with DFT and experiment, what we found is that we're actually changing through that compression the underlying potential energy surface, the underlying stability of this complex. And that's reflected in this so-called softening of this vibrational band. So we get to a point where at sufficient mechanical strain, we've destabilized the system in whatever conformation it initially was, and it flips into a different geometry. And so you can really see that if we map out the potential energy surface along this vibrational mode, that at sufficient pressure, we really are changing the underlying potential energy surface and causing a transition to happen in this material. And a lot of people now are doing some really phenomenal work in particularly in polymeric systems, where again they're applying mechanical strain, and they're allowing the atoms to relax under that mechanical strain and seeing how it changes the bonding and the chemistry there. So for example, in this system here, they're looking at the breakage of this highly strained ring, applying a strain between these two terminal methyl groups and seeing what the molecule wants to do in response to that mechanical strain. And eventually they're able to then also look at bond cleavage processes. So again, we're applying a stationary mechanical strain, and we're allowing the chemistry to change under that strain. We then have this final branch of mechanical reaction where the energy couples directly into the system itself. These are particularly hard to find good examples of, but there's some really nice ones that have come out in the last couple of years. These are not mechanical in the sense of a ball mill, but these are mechanical in the sense of a shock wave coming into the system. And what we see here, for example, in this organic crystal, that if we apply a high velocity shock wave to the crystal, we get very, very high levels of kinetic excitation in that system. That high degree of kinetic excitation will then evolve over time before chemistry happens. So we're really directly injecting that energy into the molecules in the crystal and allowing them to sort of do what they need to do in response to that high degree of excitation. And there was another really beautiful example that came out in this ultrasonic hammer example here, where they looked at the difference between a pristine crystal and a coated crystal, and again looking at the direct coupling of the shock wave into essentially a polymer coating, and looking at how the dynamic friction of the surface can lead to really high degrees of kinetic energy excitation and evolve the system over time. So again, these are very, very fast processes and very strongly coupled processes that happen at very local scales. So I guess you can sort of take a step back and say, why on earth is this just semantics? And why on earth do we actually care what's going on? It's a lot of gibberish. But I think it's really important if we think of it from the perspective of control. If we really want to gain an understanding of how do we design a system to react the way we want it to react, we really need to understand this flow chart. We really need to understand that mechanochemistry happens by creating a stress field and seeing how a system is going to relax in response to that stress field. We are going to have systems that are going to relax in terms of generating heat or in terms of generating new interfaces. We are going to have other systems that relax from activation, so a disruption of the structure. We are going to have systems that relax by reconfiguring their nuclear structure and then changing the potential energy surface. And we are going to have systems that are going to directly couple. So the reactivity is going to be very, very different. So from a very practical perspective, if we want to then think about what this looks like in terms of designing a reaction profile, if we look at a very, I guess, general kinetic profile for a mechanochemical reaction, we tend to find they look something like this, where we have some induction period, followed by some reaction phase, followed by the product phase at the end. But if we now think about mapping on these sort of fundamental properties, what we find is that this induction period tends to be dominated by these macroscopic phenomena. So it tends to be dominated by mixing, by activation, so these big scale processes. This middle bit tends to be dominated by the chemistry itself. So, is it a thermochemical reaction? Is it a mechanochemical reaction? Actually, what is causing the chemistry to happen itself? And unfortunately, what I don't have time to talk about today is this last phase then, actually, how do we control the product that's forming? How do we control the crystal form? How do we control the properties of the crystal coming out? And there's a whole different ballgame of phenomena that are happening on that scale. But again, if we really plot it out in terms of a kinetic profile, if we want to try and control this kinetics, we need to understand which of these features are contributing in which types of reactions and in which cases. So I'll quickly highlight a couple of these areas. I'll start with the macroscopic phenomena, so the mixing, the comminution, and some of the work we're doing there. So one of the big areas that is developing at the moment by us and by other colleagues around the world is the development of this time-resolved in situ measurements. So we're really trying to develop new methods that allow us to probe the mechanisms. And if we can understand something about the mechanisms of how these reactions are happening, we're trying to learn something about how can we actually exert control. At the moment, there's quite a number of different techniques that have been developed. Diffraction is probably the most famous at the moment, and Raman spectroscopy. But there's quite a number of different techniques that are appearing that are able to give us some insight into mechanochemical reactions. And why do we want so many different techniques? Well, it comes to the fact that, of course, different techniques give us very different information about the profile. And some techniques are going to be very good at telling us about macroscopic phenomena, but tell us effectively nothing about the microscopic phenomena. And other techniques are going to provide us more information on the microscopic phenomena, but not on the macroscopic phenomena. So again, if we sort of think about this, about getting a complete picture of a mechanochemical reaction, we need to combine as many methods as we can to get that complete picture. We need to do them under the most realistic conditions as we can, and at the resolution that we need to probe the phenomena that we're interested in doing. And only in that way can we really push, I think, ourselves towards this degree of control. For time's sake today, I'm not going to focus on most of these techniques. I'm just going to focus really on diffraction and what we're learning from time-resolved in situ diffraction, and then just quickly highlight at the end some of the work we've been doing in developing X-ray spectroscopy as a tool for in situ measurements. So if you haven't seen a setup like this before, it's really quite simple. We effectively take a ball mill for the diffraction experiments, we stick them in front of an X-ray beam, we shoot the X-rays through the jar, and we collect the scouting on the other side. Nothing particularly fancy about that. What we're able to do if we take our powders, so in this case, we take these two homodimers of this disulfide material, we grind them, we get, in this case, a heterodimer between a reaction between the two, and through diffraction, we are able to actually monitor that reaction. So we can see these peaks that are disappearing, being consumed, and we see new peaks that are appearing. So we can really monitor the reaction, and that allows us also, now that we have good quality data, we can actually extract quantitative quantitation for the composition of the material and really get these dynamic curves out. But what's quite exciting, not only can we now extract some of the profile for the reaction, and you do see here the sigmoid that I was talking about. So it is real. It's not just my paint skills. And it is quite general. So here's another example. So looking at this, the thiophthalate and benzamide system, again, another co-crystal. And again, through this time-resolved diffraction, we can see the consumption of certain peaks and the formation of other peaks. We can see the reaction happening. And again, we're seeing in this case a really nice induction period. But in this case, we really wanted to get to grips with actually, is something happening in this induction period, or is it just, maybe the particles need to mix or something, or is this a real phenomenon, or can we learn something about this? And it turns out now with a lot of the advances that have been made in this time-resolved in situ diffraction, not only can we get quantitative analysis, but we can actually learn a lot about the crystallites themselves. And so what we're starting to find is that this induction period is not benign. So as I said, there's a lot of macroscopic phenomena going on here. And what we're really starting to find is that this induction period is associated with an enormous comminution of the particles. We're really needing to get these particles into a state that is reactive before the reaction actually starts. So what we're seeing here, so although one of the components starts very, very small, the other component starts as very, very large crystals, and we need to get that below some critical threshold before the reaction comes. We don't yet know exactly why that is, whether it has to do with destabilizing the surfaces or whether we are actually trapping energy in this particular system, but it is very, very clear that we need to much better understand this comminution profile and what this critical threshold actually means. But we're not always seeing induction periods, and I think this is where it becomes quite interesting, is we have other systems, say this glycine on oxalic acid dihydrate, and this reaction can form one of two products, either a 1-to-1 co-crystal or a 2-to-1 co-crystal, depending on the composition of the material we're putting in. But what's really interesting here is we don't see any induction period, so it's clearly not going to be dominated by some sort of comminution process or activation process. But what's really interesting, I think, from what we're seeing from the time-resolved methods is that we can actually change the reaction profile depending on the size of the particles we're putting in the beginning. So if we start with particles of glycine and oxalic acid that are roughly the same size, we're dominating our transformation by forming the 1-to-1 product. But if we start with smaller particles of glycine and large particles of oxalic acid, we're actually getting the 2-to-1 product. And so again, this comes down to the idea of mixing. If we want to control these reactions, we need to control the mixing, because it's the interfaces between the particles that are going to dominate, that are going to control what reactions actually take place. And it turns out that we do have some degree of control over that, playing with these particle sizes. So now what we're starting to think more about is, we can probe into these macroscopic dynamics, but can we learn something maybe about how do we control these macroscopic dynamics using the milling parameters themselves? So really, can we learn something about what happens if we change a reactor parameter, what happens to the mechanism, and can we use that then to learn something about control? And just to say, there's an absolutely enormous number of parameters we can change, and I'm certainly not going to talk about all of these, and we certainly haven't explored all of these, but just to highlight that there's really an enormous landscape of things that we still don't know what they're doing, how they affect the systems, or if they affect the systems at all. But just to highlight a couple and sort of maybe highlight what these in situ methods are helping us do. So the first one, of course, is milling frequency in these ball mills. A lot of people play with, what happens if I go from 50 hertz to 40 hertz to 30 hertz? What is it doing to my reaction profile? So we've done that as well. So we were looking at this Kuhn-Van condensation between these guys here. And it turns out in this system, it's quite important to note that they're quite low melting temperature solids. And so we weren't particularly surprised to find that from diffraction, we don't see anything in the initial phases, because again, this frictional heating is leading to the melt of these solid components. And it's not until we actually get crystallization of the final product that we start to see reflections appearing. And perhaps not surprisingly, in this case, what we're seeing is that at high frequencies, so if we shake that really, really fast, we're getting a fast reaction. But if we slow it down, we're just slowing down the reaction. So we're seeing in this case, okay, we're getting a change in the reaction rate, but we're not really getting a change in the chemistry itself. That's not always the case. And that's what we found with this more complicated system. So we were looking here at the co-crystallization of 3 components here. So it's, these 3 guys here. And these ones form both binary co-crystals and a ternary co-crystal at the end. And really what we wanted to understand is this binary co-crystal, is that an intermediate on the way to the ternary co-crystal, or no, can you just get the ternary co-crystal directly from the reagents? So we started at lower frequency. So this is a 40 hertz ball milling experiment. And what we see, so in the first few stages, so again, we have this induction period. So for the first 6 minutes, nothing's happening. We're then getting formation of the binary phase and concomitantly with the ternary phase. And then the binary phase is consumed and we get left with the ternary phase. So that starts to suggest that, yeah, okay, maybe the binary phase, is an intermediate and it forms and consumed and it leads to that final product. But what's quite interesting, though, is if we go to higher frequency, we can suppress formation of that binary phase altogether. So in this case, at 50 hertz, we see the reagents, again, an induction period here for only 2 minutes now. So again, it's faster, but we don't see any formation of the binary phases, and we get direct formation now of the ternary co-crystal. So again, these are phenomena that we still don't completely understand. We suspect it has to do with the mixing and the increased mixing we're getting at high frequencies, but it does just go to show how complex some of these parameters are and how they affect different reactions in very, very different ways. We're also starting to think about how do we control with temperature? What can we learn about the role of temperature, of sort of global temperature on these mechanochemical transformations? So again, here we were looking at this co-crystallization between glutaric acid and isonicotinamide. And what we find is that under room temperature conditions, we form this form 2, but we can convert that thermally to form 1 at 363 Kelvin. So we did our in situ measurements. We see formation of form 2 if we mill it at 295 Kelvin, so nothing particularly surprising there. But what was interesting, though, is if we can raise the temperature, we can actually form the alternative polymorphs. We can generate form 1, but not at the same temperature that's needed under equilibrium conditions. We can actually generate form 1 at 10 to 20 Kelvin lower temperatures than is required just by heating the powder. So again, and what was I think quite impressive to see here is that the form 2 wasn't actually an intermediate. We just go directly to form 1. So what that starts to think is actually, are we learning something here about the excess energy or the excess temperatures that are actually being generated at these mechanical impacts? Is that the excess energy that's making up that excess the energy required to reach that thermodynamic transition, or again, are we activating the material and allowing these transitions to happen at lower temperatures than they could before? But really, from this in situ measurements, we're really starting to see that there's a really important role of these mechanical energy to play across the board of chemistry. So on the last slide on these in situ methods, I just wanted to highlight, because I think it's cool, some of the work we're doing on in situ spectroscopy. So we're really starting to recognize that, yes, we can learn a lot about the bulk crystal forms, but chemistry, of course, is the science of electrons. And we want to see, can we measure something at the electronic level during ball milling? And so we've recently developed a new setup based on dispersive X-ray spectroscopy, which allows us to measure with really high time resolution the X-ray absorption spectra during ball milling. So we used as a model system the synthesis of ZIF-8 from these two starting reagents, and we did this again, this resonant acoustic mixer, so that has just this sort of mixing of the powders, and we were able to compare what happens if we do it pure versus if we do the RAM with a ball. No drastic new insights in here, but I think it's quite interesting to see that just how different the reaction profiles can actually become, particularly both in the kinetic side, but also in the final composition of the material. So if we rely only on particle mixing, we're only achieving something about a 70 to 80% transformation. But if we add that extra amount of energy from the ball mill and the extra abrasion that the ball actually generates, we're able to push that reaction to much higher yields. So again, showing how important that efficacy of mixing can actually be in achieving efficient mechanochemical reactions. So that's all I wanted to say about the in situ stuff. There's tons of stuff out there, and if anyone's interested, there's been a lot of really good literature published over the last couple of years, both from ourselves and from colleagues around the world. So please do go take a look at that if you're interested in seeing the recent developments in that area. But as promised, I wanted to say some things about what we're doing in the microscopic domain, a little bit about how we're trying to understand really what the energy is doing at the scale of the atoms and the electrons in our systems. So the microscopic side of things. So from that perspective, the way we're starting to think about mechanochemical reactions is in terms of what the energy profiles really look like. So we're quite familiar with thermochemical reactions where we have this constant amount of energy in the system, and we allow the molecules to evolve under that constant amount of energy. But of course, if we have this ball and shaking back and forth, we don't have a nice constant amount of energy in our system. Instead, what we have are these pulses of energy followed by relaxation and another pulse and relaxation. So we have these very dynamic injections of energy into the system that we need to try and understand what they're doing to our materials. Now, it depends who you ask, but you can find numbers everywhere. But you tend to find people quoting this excitation relaxation process on the order of some pico to nanoseconds, depending on what you're doing for the ball mill itself. Different ball mills will have different spacings between pulses, but it tends to be on the micro to millisecond. And then, of course, we get the overall reaction that I was talking about from these in situ methods, which is on the order of seconds to minutes. So again, it's an incredibly complicated process to try and get to grips with. And by no means are we trying to do that at this point in time. What we're really trying to understand is what is happening within one of these pulses, and can we learn something about actually how the energy is causing chemistry to happen at a very elementary level. So we were inspired by some very, very old literature by colleagues in the US who had discussed this vibrational energy transfer models and seeing what we can do with these energy transfer models from a mechanochemical perspective. So the idea here is that as you get this dynamic compression, so you get some sort of dynamic effect on a crystal, you're going to compress that crystal in a compressive wave, and that's going to be effectively an acoustic wave. So the same as what happens if you hit the table, you can hear that acoustic wave passing through the solid. That's going to interact with some very low frequency vibrations in your material. And that excess energy has a couple of options. It can either dissipate out of the material, or it can start to interact with itself, and it can start to excite more and more higher frequency vibrations in the material until it somehow elicits a response of the molecules itself. So just before jumping into that, just to make sure everyone sort of appreciates what this wonderful line diagram is here. So this is effectively, we can think of our vibrational energy or vibrational spectrum as a ladder. So at the very low frequencies of the ladder, we have these vibrations of our crystal where we have the molecules that are just moving past one another. So it's rotations and translations of the molecules with no distortion of the molecule itself. And you tend to find that this low frequency area of the vibrational spectrum is quite densely populated. So you have a lot of vibrations that sit very, very close together. If we go slightly higher in our vibrational energy ladder, we get to this point where we have sort of a coupling between the molecular vibration, this sort of distortion of the lattice itself, and the distortion of the molecule. And the density of this part of the vibrational spectrum depends a lot on the molecular structure, but also the shape of the structure of the crystal itself. And then we get to this highest energy on the ladder, and these are the typical molecular vibrations that we think of in chemistry. So these are the bond stretches and angle bends that we know and love from chemistry. So anyone who's tried to model dynamics of molecular crystals knows that these are an absolute pain to try and get right. And so we rely a lot on benchmarking our simulations against neutron spectra. We choose neutron spectra for the main reason that there are no selection rules associated with which bands we see. So we can see all of the vibrations in our crystal and get a really good measure for, or a really good benchmark set for our simulations. So in these curves, what you'll see in black are the measured spectra from the ISIS neutron facility in the UK, and then in blue are our simulated spectra. So if we start from a very small material, so this is sodium azide, as I mentioned before, we tend to have very densely populated region here at the lowest frequency, and because we have very small molecules, we have effectively nothing in the higher frequency range. We go to something slightly more complex, a slightly larger molecule. We have, again, very densely populated low frequency area, and it starts to get a bit more populated sort of in this middle region. We go again to this larger molecule and things get a bit noisier. And eventually we get to this absolute beast of a thing, and it's just an absolute forest of vibrational bands. Now, what's really interesting at this point to highlight is sodium azide is not mechanochemically reactive, whereas as we move our way up across from left to right, we're getting more and more mechanochemically reactive. And what we find then is that the density of vibrational states seems to correlate quite nicely with that. So it starts to get us to think that maybe there really is something here about the density of vibrational bands and mechanochemistry. So the first thing we need to convince ourselves and convince you is that chemistry can happen through vibrations. So we cheated a little bit and started with a very small molecule. So this is just an azide molecule here, where we know that for chemistry to happen, the nitrogen-nitrogen bond needs to break. So we do our simulations and we stretch the nitrogen bond and we look at all the different electronic states and see what's happening. And it turns out if we can get this molecule into any of the electronically excited states, that bond wants to break and that molecule wants to fall apart. Now, of course, that's 4.5 electron volts, so that's not going to happen thermally until we remember that we're thinking about vibrations. We're thinking about what do vibrations do to our reactivity. So if we walk along the different vibrations in this N3- molecule, we find that this particular vibration, this bending mode, is actually very efficient at perturbing the electronic landscape. And we get to a point where if we can excite that vibration enough, we actually have a point where the ground state overlaps with the excited state, and we can get this sort of spontaneous excitation of the system. So that's the gas phase. So we wanted to convince ourselves that we can do this as well in the solid state. So we did the same types of calculations. And again, we're seeing even in the solid state, we're seeing that this what we've called dynamic metallization can happen if we can excite the right vibration. So again, it's not just a gas phase phenomenon. It is a phenomenon that carries over to the solid state. Right. So we know if we can get energy into the right vibration, we can do a lot of damage to the electronic structure. We can really get it into a state where it wants to react. So then what we need to do in terms of developing a model, we need to first understand or somehow come up with a way to give some sort of excitation energy that comes from a mechanical strain. We then need to think about how much of that energy is going to move up through this vibrational ladder into the molecule itself. And then we need to think about how much of that energy is actually going to be left to cause chemistry to happen. So if I start down here at the bottom, so how do we come up with an idea for how much energy is coming into the crystal? Well, we use a very, I think, drastic approximation at this point, but it turns out it's not too bad, of adiabatic compression. So what we assume is that as this dynamic impact happens, we're compressing our crystal. And as we compress the crystal, we assume that the vibrational frequencies are going to increase. So we're making the material much harder by compressing it. Now what we say is that the amount of vibrational energy that was in this system has to be the same as in this system, except that one vibrational quantum is now worth more energy. So if we can now quantify how much we're compressing the system, and if we can quantify how much these vibrational bands are going to change, we can then get a measure for how much excess energy we have in response to that compression. So we spend a lot of time doing high pressure experiments, so both experimentally and from computation, really to try and understand how materials are compressing, what's happening to the structure and what's happening to the dynamics. And so this is just an example of TNT, where we're looking at the compressibility and again, the effects of this compression on the vibrational frequencies. And that gives us then all the information we need to plug into this equation and get our excitation energy from mechanical strain. Now, I just want to highlight here, so my inorganic friends always laugh at me when I get excited that we get to 5 GPa, and they say that's absolutely nothing. And that's true for inorganic solids, but it's not true for organic solids. These are really soft materials we're dealing with. And so for TNT, for example, already at 5 GPa compression, we're getting 20% compression of the lattice. So these are not astronomical pressures we're discussing. These are really quite achievable pressures to get huge deformations of these organic systems. Okay, so we have our excitation. We have this energy that's coming in from this mechanical strain. Now we need to think how that energy is going to move. And again, we make massive approximations. So this is the approximate equation we use. And so we say that the rate of energy transfer is somehow proportional to this V term here, which tells me how strongly my vibrations interact with each other. And then we have this delta term here at the end, which tells me the number of vibrational pathways that are available to conduit that energy through the system. So effectively, how many motorways are there and how efficient are those motorways at getting the traffic through? So that's that. And then we can start to look at what these models actually look like. So here's our simulation. So we have in black, these are the simulated vibrational spectra, and on top in blue, these are the energies of the vibrational bands as we move our way through. So you can see at the very beginning, we've adiabatic compressed our system. We have all this excess energy in this low frequency area, and everything else is quite cold. We can then move the energy up into this intermediate bit, and we can move the energy up a little bit higher as we get the sort of broad excitation band that sits over top of our molecular vibrations. Then all we do is we say, okay, the only energy that's going to be captured by our system is where that excitation envelope overlaps with these fundamental frequencies. So we just basically integrate up where that blue curve overlaps with that black curve, and that gives us a metric for how much energy is there in the molecule itself. So we've looked at quite a number of systems over the years. So this is just a subset at the moment. So very different chemistry, very different crystallography, just to try and assess just how broad this model can get. So we do the adiabatic compression, we do this up pumping, and then we try and calculate how much effective energy comes into the system and see how it compares against experiment. And so here we are. So what we're seeing now very, very nicely is that systems that respond to very, very easily to mechanical strains, they're very mechanochemically reactive. They transfer huge amounts of this vibrational energy. They capture a large amount of this vibrational energy, whereas systems that are not mechanochemically reactive effectively don't capture any energy at all. So, even despite all the approximations we put into the model so far, we really are able to predict the relative mechanochemical reactivity of these elementary processes. So there's still a lot to do, but we are at a point where we're quite happy that we do have a framework that allows us to predict and I think start to understand what happens to our materials in response to mechanical insult at a very fundamental level. But that's looking at very different chemistry. So what we wanted to think about is actually, does this capture also changes in crystal structure itself? Because actually in this community, we know that the crystal form can change the mechanochemical reactivity. And there's sort of this unwritten rule of thumb that layered materials tend to be less reactive than non-layered materials. And so we wanted to see, can we capture that in our model? So we looked at this system here, where it has 3 different polymorphs. So we have a herringbone structure through to this sort of intermediate structure, and then we have a layered structure on the other side. So can we predict, do we correctly predict that this material should be more reactive than this layered material? So again, we do our simulations, we get our up pumping, we get our excitation envelope, we calculate how much energy overlaps, and this is what we get. So we now find indeed that through our up pumping model, we predict that the non-layered materials should be more reactive than the layered materials. So again, we're quite happy now that not only does this concept capture different chemistry at the molecular level, but also different reactivity at the level of crystallographic behavior. And that's now starting to get us to think more about, can we use this as a tool to start to design crystals that have a particular mechanochemical reactivity? So this is something that's just underway. We had a talented PhD student, Imogen Christopher at the University of Edinburgh, who was looking at how do we design mechanochemical reactivity, looking at this RDX compound here. This was quite interesting because it has 2 different conformations in different polymorphs, and we wanted to see, can we use actually conformation to change the reactivity of our systems? So we looked at 3 different polymorphs. So it's alpha RDX, epsilon RDX, and gamma RDX. So both the alpha and the epsilon structures have only 1 conformation, whereas the gamma has 2 different conformations. And what we find is that by introducing a second conformation, we're actually introducing a number of new vibrational bands in our density of states. And if we remember back to the neutron spectrum slide, the denser this vibrational states is going to be, the more reactive we expect our system to be. And indeed, that's absolutely what we start to see. So we can really now see that by introducing a second conformation, by designing a system that has a busier vibrational density of states, we do indeed predict the system to be much more reactive than otherwise. So it's really starting to get us to think towards crystal engineering strategies to try and control mechanochemical reactions. So just in the last minute, just to highlight, I think the direction that we're now starting to go is really trying to think, we're at a point where we're qualitatively, showing, we can predict the relative mechanochemical reactivity, but can we learn something really at the atomic level of what the atoms are doing in this model? And that really comes down to trying to solve this term here, which I won't go into detail on, but it's an absolute nightmare to do. But we can do it for very simple systems at the moment. And so we've done it for this lithium azide system. And we can actually get explicitly the phonon scattering coefficients associated with that term. And what that then allows us to do is actually then quantify how fast energy is transferring through a system and see what levels of excitation we're actually reaching. And we can then take these conditions back into our models and really start to see what this is doing to our system, to the atoms, to the electronics in our system, and try and get to grips with how the chemistry is really changing as we excite the system. So I should stress that lithium azide, again, is not mechaноchemically reactive, so we don't expect anything super exciting to happen, but it's a small enough system that we can do these calculations. But what we are seeing, that this angle bend that we know is the sort of the trigger mode for this azide molecule, and we're getting enormous deformations, 12 degrees within peak femtoseconds, which has enormous effects on the band structure. So we're really getting these systems into highly non-equilibrium states that have incredibly different chemical reactivity than the structure under equilibrium conditions. And what that's really starting to hint to us is that if we really want to understand at the elementary level how mechanochemical reactions are happening, we really can't be looking at structures that we're getting off diffractometers. We really need to understand what is the non-equilibrium behavior of these materials, and how is that changing the chemistry going forward. So with that, I come back to my first slide, just to say, we really are at a point where we know mechanochemistry is going to change the way we do industry, the way we do chemistry, the way we think about the physical sciences. And we really want to get to a point where we can control that and really make the most out of it. But to do that, we really do need to understand how these reactions are happening. I'm convinced that there are different types of mechanochemical reactions, that mechanical force is playing a different role in different types of systems. And I think it's important that we get to grips with what types of systems behave in what ways, and from that, learn how to control a particular type of mechanochemical reaction. There are macroscopic phenomena, the mixing, comminution, activation, and this is being really well studied now by time-resolved methods. There's a lot of exciting work going on there. And at the microscopic level, I think these are really amenable to atomistic simulations, some really exciting stuff going on. And I'm looking forward to seeing where the field progresses from there. So with that, there's been a lot of people involved over the years on very different aspects. So thank you to all of them, and indeed to the people who fund us and give us resources. And with that, I say thank you very much for listening, and I look forward to discussion.
Thank you so much. We have a few questions from the audience. All right, let's start with, at one point you mentioned that two different chemical species, A and B, had quite different crystal sizes, and this was important. Can you explain why the crystal size was important, and why the crystal size was different, and why that was important to the initial stages of the reaction?
I think there were two different examples I gave of that. One of them was looking at a comminution process, where we started with a one small crystal size and one large crystal size, and we needed to actually reduce one crystal size to a critical threshold before where we think we get effective mixing, or it's activation of the particles that actually allow them to react. And so we think that if we start with crystals that are too large to be reactive, that actually leads to this induction period. So we basically need to activate these materials before they're going to react. In the second case, looking at this glycine system with oxalic acid, what we actually showed is that there's not an induction period per se, but by changing the particle size, we can change the local mixing of the powder. And if we can change the local mixing, we can change which products form preferably over others. And again, it's starting to move away from the idea that we have a bulk system, but actually our reactions are happening very locally at the particle contact. So if we can change the relative mixing through particle size, for example, we can change the effective composition of our reaction zones.
Thank you. This is perhaps related. It was so interesting that the binary phase formation was affected by frequency. Could you hypothesize or suggest why that might be the case?
So again, our best guess at the moment is it has a lot to do with mixing. I think we're at a point where it may be forming, but is consumed so fast at higher frequencies that we simply don't detect it. I suspect that's probably what we're seeing, but I don't know more than that at this point.
Thank you. So you talked a lot about the importance of mixing in the early stages. What do you think about changing the shape of the milling elements, so not using balls?
Ooh, I think you get some very interesting stuff going on. Someone should do it. I think it would be brilliant to see what happens, but I can't comment more than that. So when you do it, please let me know.
All right, let's do one more. This is kind of a general one. So you focused on one of the in situ methods, and I know you didn't have time to talk about the other ones, but which of the in situ methods do you think is going to be the most promising going forward to understand the fundamental mechanisms?
I think it's going to depend a lot on what type of reaction we're looking at. So I don't think we're going to have one method that's going to give us the answer. So I think the absolute key moving forward is learning to combine methods. And there's been a lot of really beautiful stuff being done, combining spectroscopy with thermography, with diffraction. And I think that's the way forward. I think that's the only way that we're going to get the information we need.
All right. Well, I think, well, with that, we'll wrap this up, and I'll thank you again for your presentation.
Well, thank you very much.
Thank you, Dr. Michalchuk, for that excellent presentation, and thank you so much for joining us. A reminder that all of our previous speakers, some of them are shown here, are available to watch on the YouTube channel anytime, and I encourage you to check them out. We also have a great group of speakers planned for the upcoming months, and we hope that you will join us for all of them. Thank you again.